This is a video from section 4.9 in a Calculus 1 class. The problems will be taken out of the Stored Calculus textbook, 9th edition. The directions say to find the most general antiderivative of the function. But before we do, we need to recall a few things. The derivative of x to the n, this is the power rule. This is equal to nx raised to the n minus 1. The derivative of any constant is equal to 0. Okay? Now, suppose I give you the following function. Suppose I give you f of x is equal to x squared. And I want to find the most general antiderivative of the function. And so we need to ask ourselves, the derivative of what will produce x squared? Now, notice we have to think backwards. When we take the derivative, notice how we lose a degree. So notice how n went to n minus 1. When we go backwards, n minus 1 travels back up to n, right? So in other words, we start and then we add 1 to get the antiderivative that we're looking for. So to get the x squared, I need an x cubed. But if I take the derivative of x cubed, I get 3x squared. Well, how do I get rid of the 3? I need to divide by 3 or multiply by a third. So I'm going to put a 1/3 right there to compensate. And so the most general antiderivative of x squared will be 1/3 x cubed. And to capture everything, we add a constant at the end because the derivative of a constant is 0. Okay? So we're looking for a family of functions whose derivative is x squared. Suppose f of x is equal to x to the 4th. We want the derivative of what, right? To produce x to the 4th. Well, notice how 2 went to 3, 4 must go to 5. But if I take the derivative of x to the 5th, I get 5x to the 4th, but I don't want that, right? So how do I make sure that a 5 doesn't appear? I either divide by 5 or multiply by a 5th. And so capital F of x is 1/5 x to the 5th plus c. So I'm going to give you something in general. Suppose f of x is equal to x to the n. The antiderivative of f, or the antiderivative of x to the n, is capital F of x is 1 over n plus 1 x to the n plus 1 plus c. And to give you one last example here, suppose I had f of x is equal to 1 over the square root of x. But I want to write this as 1 over x to the 1/2, which is equal to x raised to the negative 1/2. So notice in this example, n is equal to negative 1/2. Okay? And so if I want capital F of x, this is 1 over negative 1/2 plus 1 x to the 1/2 plus c. Okay? Now, just keep in mind something, that if I take 1 and subtract 1/2, I get 1/2. So this is 1 over 1/2 x to the 1/2 plus c. And so therefore, capital F of x is 2x to the 1/2, or 2 times the square root of x, plus c. Okay. Now, by the way, this general formula only works as long as n does not equal negative 1. n cannot be -1 because we end up dividing by 0. Okay, now in your book, let's take a look at problem number 5. Suppose f of x is equal to 4x plus 7, and I want capital F of x. So in this problem here, remember x equals x to the first, therefore n equals 1. So I get 4 times the antiderivative of x is 1/2 x squared. And then I'm going to add 7x, right? Because the derivative of x is 1, so the derivative of 7x is 7. And then I add c. So this is 2x squared plus 7x plus c. That's it. That's problem 7. Let's take a look at problem 9. Suppose f of x is x times the quantity 12x plus 8. And we don't know how to do anything like that quite yet. But what I can do is I could distribute the x to each term within the parentheses. And when I do that, I get 12x squared plus 8x, right? And so the antiderivative, in other words, I'm looking for a function whose derivative is 12x squared plus 8x. So I'm going to get 12 times, and this is going to be 1/3 x cubed. For the first term, n is 2. And then I get 8 times 1/2 x squared. But we're looking for a general antiderivative. So in other words, we're looking for a family of functions whose derivative is 12x squared plus 8x. And so we have to add c. And then when I simplify, I get 4x cubed plus 4x squared plus c. That's number 9. Let's take a look at number 11. Suppose g of x is 4x to the negative 2/3 minus 2x to the 5/3. And I want capital G of x. Now, let's do a couple of calculations here. Remember that negative 2/3 plus 1 is negative 2/3 plus 3/3, which is equal to 1/3. So remember here, n is equal to negative 2/3. So when I add 1, I get 1/3. So we get 4 times 1 over 1/3 x to the 1/3, okay, minus 2 times, now let's do 5/3 plus 1. So 5/3 plus 1 is equal to 8/3, okay. So I get 1 over 8/3 x to the 8/3 plus c. And so if I go to simplify, I get 4 times, when I divide by a fraction, I multiply by the reciprocal. So it's 4 times 3 x to the 1/3 minus 2 times 3 over 8 x to the 8/3 plus c. And I'm done. G of x is 12x raised to the 1/3 minus 3/4 x to the 8/3 plus c. That's number 11. Let's take a look at problem number 15. So on 15, we have f of t is 2t minus 4 plus 3 square root of t, all divided by the square root of t. So this is 2t divided by the square root of t minus 4 over the square root of t plus 3 square root of t divided by the square root of t. And if I go to simplify this, I get 2 square root of t minus, I'll leave this as 4 over t to the 1/2 plus 3. In fact, it might be better. We can write that first term as 2t to the 1/2. Okay? Let's write that 1/2 a little clearer. So this is 2t to the 1/2. All right. So f of t is 2 times. Now, if I take 1/2 plus 1, I get 1/2, which is equal to 3/2, right? So I get t to the 3/2, and then I'm going to multiply by 1 over 3/2 minus, now we've already established this one. This is 4 times 2t to the 1/2 plus 3t plus c. Now, let's simplify this down a little bit further. So this is equal to, now you get 2 times 2/3 t to the 3/2 minus 8t to the 1/2 plus 3t plus c. That was problem number 15. Let's take a look at problem 19. So on problem 19, we have g of t is equal to 7e to the t minus e to the 3rd. Okay? This one's a great question, okay? Now, think about this. We're working backwards, you guys. Exponentials are always friendly because, look, the derivative of what produces e to the t? Remember, we're starting here and we're trying to work backwards. And you should be able to tell me that the derivative of e to the t is equal to e to the t. So the antiderivative of 7e to the t is equal to 7e to the t. Now remember, e to the 3rd is constant. So constants tend to go along for the ride. So I'm going to take e to the 3rd and multiply by t. And then I just add c at the end. You're done. So exponentials can be very, very nice. Let's take a look at 21. Here's another good one. Suppose f of theta is equal to 2 sine theta minus 3 secant theta tangent theta. Now, the derivative of what produces sine of theta? Okay, now, remember that sines and cosines match up beautifully, okay? So a cosine has to be involved. But we need to think backwards, right? If you guys remember, the derivative of cosine theta is negative sine theta. So how do I offset this? I need to attach a minus sign here. So when I want, well, let's do this one first. So the derivative of what produces secant theta tangent theta? Remember, think backwards. This should be secant theta. And so capital F of theta is 2 times negative cosine theta minus 3 secant theta plus c, which is negative 2 cosine theta minus 3 secant theta plus c. You're done. That's problem number 21. Let's take a look at problem number, well, we'll go in order. Let's do 22. Suppose h of x is secant squared x plus pi cosine x. And I want to find the antiderivative that I'll call h of x, capital. Think of a function whose derivative is secant squared x. Well, that's going to be tangent x. Think of a function whose derivative is cosine x. That's going to be sine x, and the pi just goes along for the ride. And then we just add c. You're done. On 23, suppose f of r is equal to 4 over 1 plus r squared minus the 5th root of t to the 4/5. Although that can be a good one too. But let's stick to this one. It's the 5th root of r to the 4th. Not t to the 4th, but r to the 4th. All right, so let's go ahead and rewrite this. And if we write this, we get 4 over 1 plus r squared minus r raised to the 4/5. But remember, 1 plus 4/5, right? So we can't forget how to take the antiderivative of polynomials or terms of polynomials, okay? So this is 1 4/5, which is equal to 9/5. Now, capital F of r is 4 times the arctangent of r, okay, minus, and then I'm going to do 1 over 9/5 r to the 9/5 plus c. But that's not enough. We have to be able to simplify that. And so f of r is 4 arctangent of r. And then I'm going to subtract 5/9 r to the 9/5. And then I add c. That's problem number 23. If we take a look at 24, and 24 is a good problem also. Suppose g of v is 2 cosine of v minus 3 over the square root of 1 minus v squared. Remember, your goal the whole time is to be able to think backwards. Now, capital G of v is going to be 2 sine of v, okay? And then we're going to go minus 3, and then I'm going to multiply by the inverse sine of v. It turns out to be the function whose derivative is 1 over the square root of 1 minus v squared. So it's 2 sine v minus 3 times the inverse sine of v plus c. You're done. And then 2 more. So if we take a look at 25, suppose f of x is equal to 2 to the x plus 4 times the hyperbolic sine of x. Now, one thing we might have forgotten is that the derivative of 2 to the x is equal to 2 to the x times the natural log of 2. Now, you got to remember we're working backwards. And so if I want capital F of x, instead of multiplying by natural log of 2, I'm going to divide by natural log of 2. So I get 2 to the x over the natural log of 2. And that'll make sense if you try to differentiate that. Okay? And then we're going to add 4 times the hyperbolic cosine of x plus c. That's a good problem. Okay? Suppose I give you number 26. Suppose f of x is 2x squared plus 5 divided by x squared plus 1. So I want to demonstrate something slick with you guys. Now, what I'm going to do is I'm going to break up the 5, and I'm going to break it up into 2 plus 3. Okay? Divided by x squared plus 1. So what I'm trying to do in the numerator is manufacture x squared plus 1. Because watch what happens. I'm going to get 2x squared plus 2 divided by x squared plus 1. Then I'm going to add 3 over x squared plus 1. Okay? Now, we still got a little work to do on this first term, but it's a really nice approach because I'm going to factor out the 2 and get x squared plus 1 on top, and I'm going to divide by x squared plus 1, and then I'm going to add 3 over x squared plus 1. Cancel. And we end up with the following. We end up with f of x is equal to 2 plus 3 divided by x squared plus 1. And the more comfortable, or the more often I should say, that you do these type of problems, the more comfortable you'll get with them. And so capital F of x is equal to 2x plus 3 times the arctangent of x plus c. And that's going to do it for this video for section 4.9. Okay, thank you.